In the last lecture, we have looked at the direct information provided by various experimental techniques. What we are going to now focus upon is, there is a fundamental difference. See, when you do a course in strength of materials, you find out what is stress, and your focus is essentially based on stress at a point. Rarely you come across how does this stress vary from point to point, and you have ever had an opportunity in a first level course to even plot how the variation is and look like, because you are concentrating more on stress at a point. At best you would have done a Mohr circle where you find out as a function of orientation how does this stress components vary at a point of interest. On the other hand, if people are using numerical technique, you have very many post processors that have been developed which actually display the result in a form where a human being can react. If you see red color, you find it is more, so there is a danger signal, you have to do some correction about it. So only when you had come to numerical technique and with post processors, you have been able to see those, and that happened somewhere in 80s, you can say. Though computers are developed in 1960s, the post processors developed for plotting results became user friendly and became easily available only in 1980s. But if you look at experimental technique, they have always been giving only whole field information. They were not giving point by point. Most of the optical techniques give whole field information. So as an experimentalist, when you want to go and look at, you need to get sensitized how to react to these optical patterns. So for example, you go to a doctor and then he finds out your temperature, he finds it is 105, he should react immediately that you have a very high temperature. Even as an individual, you should know that you should react, you should take some ice and put some cold bath and remove the temperature. He should not go to the encyclopedia of medicine and then find out what does 105 degree means, then you will never go to the doctor. So numbers are very important in engineering and you should react to that. So similarly, when you come to optical techniques, you should react to, when you see high density fringes, you should get an understanding that there is something wrong. I mean, the stress levels are very high, and you should also develop certain affinity towards how these patterns develop, how they are distributed, what kind of qualitative information you can get out of it. So the idea here is, although analytical methods could provide stress, strain and displacement fields in general, from a course on mechanics of solids, one has awareness of only the stress field. This is another point which I would like to mention. We have said that you want stress components, strain components and displacement components. You go back and look at your notes in strength of materials, except deflection of beams, you would have only worried about stress information everywhere. So you learnt in a first level course only those pertinent information which is required for you to apply in normal simple problems where you come across in and around you. Only when you go to advanced level of studies where you would like to make certain decisions based on strain or based on displacement, then you look for how to get all this information. Though you have solved all these problems, you may not have the solution of strain field or the displacement field, because I have already pointed out that experimental methods do not give only stress. See, if you go to strength of materials, you find out by force balance and equilibrium condition, you find out only stress. And if you go to theory of elasticity, you have stress formulation. So you first find stress. By the time you find out the stress, you are tired, you do not want to look at strain and displacement. Okay. And if you go to finite elements, essentially there are methods which use stress, but essentially it is a displacement based. Initially you find out displacement, then your software itself converts the displacement into strain and also converts this as stress, and with modern post processors it also shows the variation like what you see in an experimental technique dynamically. Okay. So what you need is, when you want to have appreciation of experimental technique, for simple problems you also need to know stress field, strain field and displacement fields. So you become sensitive to appreciating field information rather than point information. See, while developing stress as a tensor, you need to know how does it change from plane to plane. If you take a point, how does it change from plane to plane is very important. So, from that was the focus, and you know a rudimentary knowledge, that is stress concentration, you do not go beyond that. But once you come to experimental technique, you need to have this appreciation, and I want you to be good engineers and not refer the reference books for simple things. Okay. So, what we are going to look at is, we are going to look at in the subsequent slides stress as well as strain and displacement information for some of the benchmark problems, because it is always better you go from known to the unknown. You have already done some of these problems in your course in strength of materials, and look at again those problems with a different perspective, see what all you have got and how the contours will look like. So, this will also indirectly say that whatever the contours I have seen in an experiment, by pattern matching you can say that yes, if I plot sigma 1 minus sigma 2, it looks like this, and I see the same thing there. So, this should be sigma 1 minus sigma 2, I can go. And I have taken in all 5 problems, and they are also done with a graded level of complexity. So, one of the simplest problem which I have taken is beam under 4-point bending. That is the first problem to start with, and why I have taken this is, you have closed form solution by strength of materials. So, that is what you have done in a course in strength of materials. So, you know completely the story of beam, leaving the points of loading regions away from it, you know what happens in beam, and I am sure you would have just looked at stress field. I do not think you might have looked at strain field or displacement field, we would see all that. Okay. Then the next problem is cantilever beam. Why I have taken this is, see in a cantilever, though you apply Flexure formula and so on, you actually have shear which makes the planes do not remain plane before and after loading. Because shear effects and bending effects are not coupled, still the solution from strength of material is valid, and that is why good books term this as engineering analysis of beam. There is a subtle difference between analysis of beams, where you say mathematically correct, engineering analysis, and understand engineering means approximation. We cannot do engineering without approximation, and you do that right at cantilever beam. And you know, you have done cantilever beam, simply supported beam, clamped beam, all those problems except beam under 4-point bending, they are all only engineering analysis. So, you make approximation. And the next problem is disk under diametral compression. See what you have is, this is what we had seen in the last class. I have a shape like this. When I have the bar, when I pull it, strength of materials is good. The moment I put a hole, I cannot do by strength of material. Suppose I change the shape to a circle and I put compression, and this is the most celebrated model that you use in photoelasticity. You do not have a solution from strength of materials, but you can definitely find out a closed form solution from theory of elasticity. I can use Boussinesq solution and get the stress field at every point in the model. Every point in the model I can find out. I can find out at every point in the model. And this solution is also very important for you to note it down. Then I will have clamped circular disc with a central load, and I will show this little bigger. And what you have here is, I can find out W, that is outer plane displacement, dou W by dou x is slope, dou square W by dou x squared is curvature. Similarly, I have curvature in the other direction, dou W by dou y and dou square W by dou y squared. Because this is a standard benchmark problem when you want to go and establish techniques to measure outer plane displacement. and for this also you can get the solution available from theory of elasticity. It is possible to find those solution. And finally, we come back to our celebrated problem, spanner, tightening a net, and due to complex nature of the geometry only a numerical solution is possible. Experimental solution is always possible for all these problems. Understand this, analytical problems gives you conceptual understanding. If you are able to solve it analytically, they are the best, but the reality is beyond certain simple geometry and simple loading conditions, analytical methods are not possible to attack all problems on hand. Numerical methods solve it approximately. When you come to experimental methods, it gives you truth. If my numerical method does not match with experiment, I should go and find out have I applied the boundary condition correctly. If my analytical method does not match with experiment, then I should go and verify whether the analytical method has made certain approximation, and you have to refine that approximation. So, finally experimental methods are the truth, it provides you truth. So, you have to judge the other techniques based on experimental methods alone, and for all these cases relevant experimental contours also we will have a look at it. So, the idea is to get yourself sensitized on appreciating whole field visual information. I want you to react. See, as towards the end of the course we will see the necessary optical arrangement, we will also mathematically develop how these contours are, all those development we will do, but this knowledge will become reinforced even to start with for simple problems how these contours look like. That gives a certain level of familiarity and also makes you comfortable for you to go and involve in yourself in the experimental technique. And in the subsequent classes we will see for simple problems to start with what each experimental technique will give. Not only this, we will also look at the stress field, strain field as well as displacement field. In this lecture we have discussed a graded list of problems of different complexity which serve as benchmark problems in solid mechanics.